So in this problem, we have a person shooting a basketball at a 35-degree angle at 12 meters per second, and they are 2.4 meters tall. The basketball hoop is 10 feet or 3.05 meters tall, and we want to find the distance between the person and the basketball hoop. Well, first thing we might think to do is use the second kinematic equation, x equals x initial plus velocity initial times time plus 1/2 acceleration times squared. And if we input this, would be the equation here, then we input the initial x position, which is right here, and that would be 0. And then the initial velocity, well, we only have the overall velocity, but we need the x velocity. We need it in terms of x, so we need to split it up into its individual vectors. Sorry, let me just get the camera focused. We need the individual vectors. So to get this bit here, we'll need to multiply this angle, this over here, like just this line, or what this line represents, over this line here, which we told meters per second, could also be referenced in terms of the angle as a over h, or the adjacent over hypotenuse, which is also known as the cosine of whatever angle we're dealing with. And if we multiply that, or cosine of 35, by 12 meters per second, or the hypotenuse, the h is going to cancel out and just give us the a. So it's just going to give us the x velocity. So therefore the initial x velocity over here is equal to 12 cosine of 35. So we can input that in there, and we continue along with the acceleration being 0. But since the acceleration is 0, because we are not counting air resistance, this whole term right here is just going to be equal to 0. And then we're left with this equation right here, which is just basically our first equation. But what we don't know here is time. We don't have enough information for time. So what we can do is use how much information we have. We can use our exact same equation, but in the y direction, or in the y-axis. So the final y value would be 3.05 meters, which is going to be equal to the initial y value, which is 2.4 meters, plus the initial y velocity, which in conjunction with the initial x velocity would just be sine, because it'd be opposite over hypotenuse, which would just be here over the hypotenuse, the upwards length. So we get 12 sine of 35. And since we have 12 sine of 35, then we're going to have to multiply this by time. So we get time here. Now we want our 1/2 at squared. So we're going to have plus 1/2. And acceleration due to gravity, we'll be taking it as negative downward. So we'll get negative 9.8 times time squared. What this can be turned into is a quadratic equation. As you can see, t squared and t, and they're constants. So we could just subtract this 2.4 from the equation, and we'll just get rid of units for now, because we won't be dealing with them, because we'll add units back in. In some questions, you will need to work with units in the actual question, but for this one, we can just go back to normal. So 3.05 minus 2.4 is 0.65, which is going to be equal to 12 sine of 35 times t plus 1/2 negative 9.8 times t squared. We can simplify this again, and I'll just simplify it and turn it into a quadratic equation to get 0 equals negative 4.9 t squared plus 12 sine of 35 t, then minus this 0.65. And now that we have that as a quadratic equation, we can either put this into a calculator or solve for it. We will get two values when we solve for t in this. One will be 0.3 or something like that. I'll put it into my calculator now and I'll get back. So when I input these values into the calculator, we end up with these two values. We end up with roughly 1.3 seconds and roughly 0.1 seconds. But the value that we are going to, the one that we are going to want to use is the larger one, because the smaller one is just how long the basketball takes to reach the same height as it, but not at the same position. So that could be right here in the motion. And it takes 0.1 seconds to reach here, but it takes 1.3 seconds for it to reach in the actual basket. So we can take that value that we now have there. So we'll write, well, I'll just move my calculator over. We will write time as being equal to 1.302860. I'm just going to cut off, I'm just going to round it, because this will give us a high level of accuracy, but also means I won't have to like continually write out all the whole entire number again for simplicity. So now that we have this, we can plug this into the original equation that we were going to use, because now we have the value of time. So we will get x is equal to the initial value, which is 0, so we don't need to put it there. The initial x value is now going to equal 12 cosine of 35 times t, which we have it there now, plus 1/2 a. The acceleration, due to air resistance being negligible in this example right here, will be 0. So this whole term right there will just cancel out to 0, and then we're left with just this equation. So I'll plug this into a calculator, and we will get. If I just type 1.3028601A187. So I've just typed out the whole thing for now. And we're going to multiply that by 12 cosine. You have to put brackets on the TI Inspire, because then it won't, otherwise it won't give it the exact value. Now we have that, and we get 12.806, we'll round it to the nearest number, x equals 13 meters. So therefore, right here, x is equal to 13 meters, which is the correct answer in the textbook, or here's the exact picture in the textbook. I'm doing question 61A, and there you go. That's how you would use the kinematic equations to solve this.